Inside a low-brick testing shed on the edge of the Winton Engine Works, a single diesel engine turns over on a steel test stand. No windows, no daylight. Just the concussive thud of 6 cylinders finding their rhythm, one after another, until the sound settles into a steady driving pulse that vibrates through the concrete floor and into the souls of the engineers standing nearby. This engine will never see open water. Not yet. It's bolted to a frame, feeding data to men with clipboards, its exhaust venting through a pipe cut into the roof. But if it passes, a version of it will be lowered into the hull of a United States Navy submarine, sealed inside a steel tube, expected to run for hours beneath the surface of the Pacific, keeping men alive on nothing but its own reliability. That is the job it was built for. It is not the job that will make it famous, because the same engine turning on this stand in Cleveland, the same architecture, the same compact power-to-weight breakthrough the Navy is betting on, is about to be handed a second assignment, one that has nothing to do with submarines at all. But the real story of Winton is not just about an engine builder that supplied the U.S. Navy. It is the story of a company that succeeded so completely somewhere else that the Navy became an afterthought, and what happened when General Motors decided the railroad, not the ocean, was where the future was. Every week on this channel, we dig into the names and machines that once defined American industrial power. The engines, the shipyards, the factories that built an empire, and then watched the ground shift beneath them. Some collapsed. Some got swallowed by bigger companies. And some, like the story you're about to hear, didn't fail at all. They just walked away from the fight everyone expected them to win. If stories like that interest you, consider subscribing. Now, back to Cleveland. The story begins not with nostalgia, but with a specific place in Cleveland, Ohio, in 1897. At the time, Cleveland was one of the beating hearts of American industrial ambition, a city of foundries, machine shops, and self-taught engineers who believed that anything running on steam or fuel could eventually be made faster, lighter, and better. The automobile was still a novelty in most of the country, a rich man's curiosity more than a serious mode of transportation. But in a handful of workshops scattered across the Midwest, men were racing to prove that gasoline engines could do more than power a bicycle. They could carry a person down the street without a horse in front of them. One of those men was Alexander Winton. Winton was not born into wealth, and he was not a dreamer chasing an abstract vision. He was a Scottish-born machinist who had immigrated to the United States as a young man, worked his way through shipyards and machine shops, and built a reputation as someone who understood metal, tolerances, and mechanical reliability better than most men twice his age. Before he ever built a car, he built bicycles, founding the Winton Bicycle Company in Cleveland in the early 1890s, at the height of America's bicycle craze. It was steady, profitable work. It was also, for Winton, a stepping stone, because Winton had noticed something the bicycle boom couldn't satisfy: a growing unmet demand for personal transportation that didn't rely on a horse, a rail line, or a fixed schedule. People wanted to go where they wanted, when they wanted. In 1897, Winton pivoted his company entirely, founding the Winton Motor Carriage Company and turning his mechanical obsession toward the internal combustion engine. The gamble paid off almost immediately. Winton's automobiles were, by several accounts, among the first gasoline-powered cars sold commercially in the United States. Precise, well-engineered machines, built by a man who treated every bolt and bearing as a matter of personal reputation. Winton himself drove his own vehicles in long-distance endurance races, using the results as proof of durability more persuasive than any advertisement. His cars developed a reputation for being built by someone who actually understood how they worked, not just how they looked. But the automobile industry Winton helped pioneer was about to change in a way he never fully adapted to. As the 1900s wore on, a new generation of manufacturers, chief among them Henry Ford, began chasing volume, standardization, and price, turning the automobile from a precision machine into a mass-market product. Winton, ever the engineer, kept building cars the way a craftsman builds an instrument, carefully, deliberately, and in smaller numbers than the market increasingly demanded. By the early 1910s, the writing was on the wall. The Winton Motor Carriage Company could not outford Ford. So Winton did what he had already done once before. He pivoted again. Rather than compete in a car market being reshaped by the assembly line, Winton redirected his company's engineering talent towards something with far less competition and far higher technical barriers to entry: heavy-duty diesel and gas engines for marine and industrial use. The company reorganized as the Winton Engine Company, and later the Winton Engine Corporation, applying the same obsessive mechanical precision that had once gone into automobiles toward a completely different unmet need, one the rest of American industry was only beginning to recognize. That need had a name: the diesel engine problem. Ships, submarines, and industrial plants all needed a compact, reliable power source that could run for extended periods without the constant maintenance and fuel inefficiency of steam. Diesel technology, still relatively young and dominated by heavier, slower European designs, hadn't yet been solved for American conditions, particularly for a demanding, safety-critical customer that was about to come calling: the United States Navy. Hunting for a new generation of submarine propulsion as the interwar years pushed naval engineering in directions no one had fully mapped yet. Alexander Winton, the man who had once raced his own automobiles down dirt roads to prove a point, was no longer building cars for the public. He was building the engines that would soon be lowered into the hulls of American submarines, and without anyone in Cleveland quite realizing it yet, laying the groundwork for a second American industrial empire that would have almost nothing to do with the sea at all. By the late 1920s, the United States Navy had a problem. It could not engineer its way around with brute force. It needed submarines that could travel farther, dive deeper, and stay on station longer than the boats built during the First World War. And every one of those improvements depended on a single component buried deep inside the hull: the diesel engine. To understand why this mattered so much, it helps to understand what a submarine engine actually has to do. A diesel-electric propulsion system is a setup where a diesel engine doesn't directly turn the propeller. Instead, it drives a generator that either powers electric motors for propulsion or recharges massive banks of batteries. On the surface, running on diesel power, a submarine could travel long distances and charge its batteries at the same time. Submerged, it switched entirely to those batteries, running silent on electric motors alone. The diesel engine, in other words, wasn't just a power source. It was the only reason the batteries had any charge left to fight with. That made reliability non-negotiable, in a way almost no other industrial application demanded. A truck engine that failed left a driver stranded on the side of a road. A submarine engine that failed left 60 men trapped inside a steel hull, possibly hundreds of feet underwater, with no way to recharge the batteries, keeping them alive, and no way to surface safely if the enemy was watching. The U.S. Navy's Bureau of Engineering understood this math perfectly, and by the mid-1920s, it had grown deeply frustrated with the diesel engines available to it: heavy, imported European designs, and a handful of domestic engines that were underpowered, prone to cracking under sustained heat, or simply too large to fit the tight confines of a submarine hull without eating into space needed for torpedoes, crew, and batteries. What the Navy needed was an engine that solved a specific brutal trade-off: enough horsepower to move a several thousand-ton submarine and recharge its batteries quickly, packed into a size and weight the hull could actually accommodate. Built to run for thousands of hours without the kind of catastrophic failure that, at sea, meant death. This is where Winton Engine Corporation entered the story, and where the fight for the submarine diesel contract became, in effect, a two-company race. The other serious contender was the Hooven, Owens, Rentschler Company of Hamilton, Ohio, a firm with deep roots in heavy industrial engine manufacturing, betting its own reputation on a competing diesel design for the same Navy contracts. HOR's approach leaned on proven heavy industrial engineering scaled down for naval use. Winton's approach, shaped by Alexander Winton's decades of obsessive precision engineering, leaned in a different direction entirely. A lighter, faster revving two-stroke diesel design that traded some of the brute force durability of heavier engines for a dramatically better power-to-weight ratio. A two-stroke diesel engine is a design where the engine completes a full power cycle: intake, compression, combustion, exhaust, in just 2 strokes of the piston instead of 4, firing twice as often for a given engine speed and squeezing more power out of a smaller, lighter package. For a submarine designer fighting for every cubic foot of hull space, that difference mattered enormously. A 2-stroke Winton engine could deliver comparable horsepower to a larger 4-stroke rival, while taking up meaningfully less room and weighing less space and weight. The Navy could instead spend on fuel, torpedoes, or crew habitability. It was not a risk-free choice. 2-stroke diesels of the era ran hotter, cycled more stress through their components, and demanded far tighter manufacturing tolerances to avoid the kind of cracking and premature wear that had plagued earlier American diesel attempts. Winton was, in effect, betting the company's naval future on a harder engineering problem, one that rewarded precision and punished shortcuts. In 1930, that bet attracted the attention of an entirely different kind of company: General Motors. GM, flush with capital and expanding aggressively beyond the automobile business, under the influence of engineers like Charles Kettering, saw something in Winton's engine work that went beyond a single Navy contract. Diesel power, GM's leadership believed, was not a niche military curiosity. It was a technology on the edge of transforming multiple industries at once. From marine propulsion to something almost nobody else in Detroit was seriously considering yet: railroads. General Motors acquired the Winton Engine Corporation outright in 1930, absorbing its Cleveland engineering talent, its manufacturing base, and, critically, its 2-stroke diesel expertise into the growing GM industrial empire. For the U.S. Navy, the acquisition changed very little at first. Winton engines, now backed by General Motors' manufacturing muscle and capital, continued development at a pace the company could never have sustained alone. Reliability improved. Output climbed. Engineers who had once worried about hull space penalties now had access to GM's metallurgical research, its precision manufacturing tolerances, and its deep bench of engineers accustomed to solving problems at industrial scale. The proof point came in the form of a contract that mattered, as the Navy moved forward with its new fleet-type submarine program. In the early to mid-1930s, the design lineage that would eventually mature into the Gatto-class boats that fought the Pacific War a decade later. Winton diesel engines, now under General Motors' ownership, secured a place in the Navy's propulsion plans, competing directly against HOR's rival design for the same hulls. It was, by any measure, a validation of Alexander Winton's original bet that the harder, lighter, higher revving 2-stroke architecture was the correct answer to the Navy's brutal underwater math. Winton diesel engines were now officially part of the machinery keeping American submariners alive beneath the surface of the Pacific. Engines conceived by a Scottish immigrant machinist who had started out building bicycles, refined through 2 industry pivots, and now backed by the largest industrial corporation in the United States. But inside General Motors, in offices far from Cleveland's testing sheds, a very different kind of opportunity was already taking shape, one that had nothing to do with submarines, torpedoes, or the U.S. Navy at all. And it was about to pull Winton's engineering legacy in a direction no one at the Bureau of Engineering had anticipated. While Winton's engineers in Cleveland refined diesel engines for the Navy's submarine fleet, a parallel story was unfolding inside General Motors, one that had started almost as a side experiment and was about to become something far larger than anyone at the company's Detroit headquarters had planned for. The American railroad industry in the early 1930s was still overwhelmingly a steam-powered world. Steam locomotives were massive, iconic, and deeply embedded in the national imagination, but they were also inefficient, labor-intensive, and expensive to maintain. A steam engine needed to build up pressure before it could move, required constant refueling with coal and water, and demanded armies of maintenance crews to keep its boilers, fireboxes, and moving parts from failing. Railroads had lived with these costs for a century because there was no serious alternative. Diesel-electric propulsion, the same core technology GM had just acquired through Winton, was about to change that math. A diesel-electric locomotive works on a similar principle to a diesel-electric submarine. The diesel engine doesn't turn the wheels directly. Instead, it drives a generator that produces electricity, which then powers electric traction motors connected to the wheels. The advantage over steam was dramatic. A diesel-electric locomotive could start instantly, required far less maintenance, burned fuel more efficiently, and, critically for railroads watching every dollar during the Depression, could run substantially longer between overhauls than a steam engine's boiler and firebox could tolerate. General Motors leadership, particularly Charles Kettering and GM President Alfred Sloan, recognized something the rest of the American railroad industry had not yet fully grasped. The same compact, high-output, two-stroke diesel architecture Winton had developed for submarines could, with modification, be scaled and adapted into the power plant for a new generation of American locomotives. In 1930, the same year GM acquired Winton, the company also formed the Locomotive Corporation, an internal railroad division designed to develop diesel-electric locomotives using engines drawn directly from Winton's engineering lineage. At first, this was a modest, experimental business, a handful of diesel-powered switcher locomotives in the rail cars, built in limited numbers, mostly for railroads willing to gamble on unproven technology. But the engineering DNA running through these early locomotives was unmistakable. The same two-stroke diesel principles Winton had refined for the Navy's submarine contracts, now scaled up and reconfigured to survive not the pressure of the deep ocean, but the punishing continuous duty demands of hauling freight and passengers across thousands of miles of American rail. The engine at the center of this new business had a name that would come to define an era: the Winton 201A. The 201A was a direct descendant of the submarine diesel work happening in Cleveland, a two-stroke design refined for higher continuous output, adapted specifically for the unique demands of rail traction, where a submarine engine needed to run intermittently, in bursts, recharging batteries between periods of quiet underwater running. A locomotive engine needed something different, the ability to run for hours at a stretch, at high sustained load, hauling tremendous weight across track grades that never let up. GM's engineers found themselves solving a variant of the exact same problem the Navy had posed years earlier: how to extract maximum reliable power from a compact, high-revving diesel architecture, just with an entirely different customer's failure conditions in mind. One man, more than almost anyone else at General Motors, came to embody this shift. Inside GM's research division, engineers working under Kettering's broader mandate to modernize American transportation began quietly making the case, year after year, that the locomotive business represented something the submarine contracts never could: scale. The U.S. Navy, even during periods of active fleet expansion, might order engines for a few dozen submarines in a given year. American railroads, by contrast, operated tens of thousands of locomotives nationwide, nearly all of them steam-powered, nearly all of them approaching the natural end of their operational lives, and nearly all of them representing a potential diesel conversion sale. It was not that anyone at GM had decided the Navy no longer mattered. It was that the math of the locomotive opportunity was becoming impossible to ignore. Through the early to mid-1930s, GM's Locomotive Corporation began building its case with real-world results, rather than just internal advocacy. Diesel switcher locomotives, employed for yard work at major freight terminals, demonstrated dramatically lower operating costs than their steam counterparts. Railroad executives, men who thought in terms of cost per mile and maintenance hour totals, not romantic attachment to steam, began paying attention. And the companies that had once dismissed diesel power as a Navy curiosity, fit only for something as specialized as a submarine, started asking Locomotive a very different question: could this technology be scaled up enough to replace steam locomotives on main passenger and freight lines, not just in the switching yard? The answer arrived in dramatic fashion. Locomotive-powered locomotives began pulling high-profile passenger runs across major American railroads through the mid-1930s, each one a public demonstration engineered as carefully as any Navy proof point, proof that diesel-electric power, born from a submarine propulsion program, could outperform a century of steam engineering on America's most prestigious rail lines. Every one of those locomotives carried, buried deep in its engine block, The same fundamental architecture Alexander Winton's engineers had once designed for a very different kind of vessel, one that operated beneath the ocean instead of across the open plains of the American Midwest. The submarine and the locomotive, it turned out, shared more engineering DNA than anyone in Cleveland or Detroit had initially imagined, and by the mid-1930s, it was becoming increasingly clear inside General Motors which of those two applications represented the company's real future. By the middle of the 1930s, General Motors diesel engineering, the same lineage that had started in a Cleveland testing shed built for submarine engines, had become something larger than a product line. It had become an infrastructure embedded on two completely different fronts of American life at the exact same time. On the naval side, that infrastructure was quiet, disciplined, and largely invisible to the public. Winton-descended diesel engines, now manufactured under General Motors' industrial umbrella, were being installed across a growing portion of the U.S. Navy's expanding submarine fleet, around naval shipyards in Groton, Connecticut, and Mare Island, California. A specialized workforce had emerged, technicians trained specifically on GM's diesel architecture, familiar with its tolerances, its failure points, its maintenance rhythms. This was not a business built on flashy public demonstrations. It was built on something quieter and, in its own way, more valuable. Trust. Submarine crews trusted these engines with their lives every time they submerged, and that trust had been earned through years of incremental reliability improvements, not marketing. On the railroad side, the infrastructure being built was the opposite of invisible. It was loud, public, and increasingly impossible for the American railroad industry to ignore. Locomotive's diesel-electric locomotives required an entirely new service ecosystem to support them, a network the old steam-era railroad workforce had never needed to build. Steam locomotives had been serviced by roundhouses full of boilermakers, firemen, and mechanics trained in 19th-century steam technology, a trade passed down through generations of railroad families. Diesel-electric locomotives demanded something completely different. Technicians who understood electrical traction systems, generator maintenance, and the same high-precision two-stroke diesel principles that had once been the exclusive domain of Navy submarine engineers. General Motors, recognizing the opportunity, began establishing dedicated training programs and service centers for railroad operators transitioning to diesel power, effectively exporting the specialized engineering knowledge born in Cleveland's submarine engine program directly into the American railroad workforce. The signature moment, the one that fixed diesel-electric power permanently in the American public imagination, arrived on May 26, 1934. That day, a sleek stainless steel diesel-powered train, called the Pioneer Zephyr, built for the Chicago, Burlington, and Quincy Railroad, and powered by a Winton lineage engine, completed a record-breaking non-stop run from Denver, Colorado, to Chicago, Illinois, covering roughly 1,015 miles in just over 13 hours, a pace and distance no steam locomotive of the era could match on a single tank of fuel. Newspapers across the country covered the run breathlessly. Crowds gathered along the tracks just to watch the silver train streak past. For a depression-weary public accustomed to associating American industry with layoffs and bank closures, the Pioneer Zephyr's run felt like proof that American engineering still had something extraordinary left to offer. It is worth pausing on the ritual this created, because it says something about how completely diesel power reshaped daily American life. Across small towns along major rail lines throughout the mid to late 1930s, it became a recurring Saturday morning scene. Families gathering at the local station, children counting the minutes until the diesel-powered passenger train came into view, the low mechanical growl of the engine announcing its arrival long before the train itself appeared around the bend. It was a sound and a spectacle that had, within just a few years, become as embedded in small-town American ritual as the church bell or the factory whistle. And at the heart of that spectacle sat an engine architecture that had been born just a few years earlier, inside a submarine propulsion program almost no one in that crowd had ever heard of. By the late 1930s, the numbers told an unambiguous story. Locomotive's diesel locomotive sales were climbing sharply year over year. while orders for new steam locomotives across the American railroad industry were beginning a decline from which they would never recover. GM's diesel engine production, spread now across submarine contracts, locomotive contracts, and a growing list of industrial and marine applications, had made General Motors, almost without the broader public realizing it, the most important diesel engine manufacturer in the United States. Inside General Motors' leadership, this was the moment collapse of any kind, in either direction, seemed unthinkable. The Navy relationship was stable and prestigious. The railroad relationship was growing explosively. Both businesses drew from the exact same well of two-stroke diesel engineering expertise Alexander Winton had built decades earlier out of a Cleveland bicycle shop. It felt, to everyone involved, like a company that had found the rare, enviable position of dominating two entirely different industries at once, with no reason to believe it would ever have to choose between them. That confidence was about to be tested. But finding the top of the market is dangerous, because that is exactly where the rules begin to change. By the late 1930s, General Motors' diesel engine business had grown into something almost too large for its own internal structure. What had begun as a single Cleveland engine works, supplying a single customer, had split into two increasingly distinct worlds operating under one corporate roof: a naval propulsion business built on strict military specifications, small production runs, and life-or-death reliability standards, and a railroad locomotive business built on volume, speed of delivery, and the relentless commercial math of a rapidly expanding civilian market. For years, General Motors had managed to serve both worlds using the same engineering lineage, the same manufacturing base, and largely the same pool of engineering talent. But the deeper Electromotive's locomotive business grew, the more that arrangement began to strain against its own success. The Navy's engineering demands were not slowing down. If anything, the Bureau of Engineering was pushing for tighter tolerances, higher output, and more rigorous testing as war clouds gathered over Europe and Asia. At the very same moment, the railroad business was demanding the opposite kind of attention: faster production timelines, standardized designs, and manufacturing capacity scaled for an entirely different customer base counted in the thousands, not the dozens. Two businesses, one engineering lineage, and a corporate parent that was about to be forced to decide in a way it had never had to before, where its most talented engineers, its factory floor space, and its future capital investment truly belonged. The choice General Motors was about to make would not look from the outside like a company in crisis. There would be no bankruptcy filing, no dramatic collapse, no plant closure making headlines. But for the U.S. Navy, and for the engineering legacy Alexander Winton had built from nothing, the decision GM's leadership was quietly reaching would change everything. The pressure that began reshaping General Motors' diesel empire in the late 1930s did not arrive as a single crisis. It arrived as a series of compounding, entirely reasonable business decisions, each one defensible on its own terms, each one quietly pulling the company's engineering priorities further away from the U.S. Navy. The first pressure was technical, and it cut to the core of what had made Winton's original two-stroke architecture so attractive in the first place. Submarine engines and locomotive engines, despite sharing a common ancestor, were diverging in their engineering requirements with every passing year. The Navy's Bureau of Engineering, watching global tensions escalate through the late 1930s, was demanding submarine diesels capable of higher sustained horsepower, tighter reliability margins, and more rigorous shock and vibration testing than any civilian railroad customer would ever require. Electromotive's locomotive engines, meanwhile, were being optimized for an entirely different set of priorities: standardized mass production, faster manufacturing turnaround, and components designed for ease of field replacement across a rapidly growing fleet of civilian customers. What had once been a single, unified engineering platform was splitting, quietly, into two specialized branches that shared a family resemblance but were solving increasingly different problems. This created a real dilemma for General Motors' engineering leadership. Every engineer assigned to refine submarine-specific improvements was, by definition, an engineer not available to accelerate the locomotive business, and the locomotive business was where the company's own sales figures said the growth actually was. It would have been easy in hindsight to call this short-sighted. It was not. It was the entirely rational response of a company allocating scarce technical talent toward the market, delivering the clearest, fastest return on investment. The Navy contracts were prestigious. The railroad contracts were transformative. The second pressure was regulatory and institutional, tied directly to how the U.S. military procurement system worked. Naval engine contracts came bundled with extensive government oversight, inspection requirements, documentation standards, and a Bureau of Engineering that answered not to shareholders, but to Congress and the fleet. Every submarine engine GM produced had to satisfy a level of institutional scrutiny that a civilian locomotive sale to the Santa Fe or Union Pacific simply did not require. That oversight was not unreasonable. It existed because the cost of naval engine failure was measured in human lives, not maintenance downtime. But it also meant that, dollar for dollar, engineering hour for engineering hour, the Navy business was structurally more expensive to service than the exploding civilian locomotive market, even before accounting for the smaller order volumes the Navy could realistically place. The third pressure came from inside General Motors itself, and it was, in some ways, the most decisive of all. Capital allocation at a parent company answering to shareholders, not the fleet. General Motors' corporate leadership, men like Alfred Sloan, who had built his reputation on rigorous data-driven business management, evaluated its diesel engine investments the way it evaluated every other division, by return on capital, and by nearly every measure available to GM's leadership in the late 1930s. The locomotive business was winning that comparison decisively. Electromotive's addressable market, tens of thousands of aging steam locomotives across the entire American railroad system, dwarfed anything the Navy's submarine program could offer, even accounting for the Navy's accelerating wartime buildup. None of this reflected incompetence, and none of it reflected any diminished respect for the Navy relationship that had, in a very real sense, made Electromotive possible in the first place. It reflected a company doing exactly what large, well-run American corporations were supposed to do, following the clearest path to growth, and organizing its internal structure to support that path as efficiently as possible. That reorganization arrived in a decision that, on the surface, looked like nothing more than a routine corporate restructuring: the formal separation of General Motors' naval and industrial diesel engineering from its railroad locomotive business into two distinct operating divisions. In 1938, General Motors established the Cleveland Diesel Engine Division, consolidating the company's submarine and naval propulsion engineering, the direct descendant of Alexander Winton's original two-stroke diesel work, into its own dedicated corporate entity, based in Cleveland, separate from the increasingly dominant locomotive business now operating under the Electromotive banner. On paper, it was simply an organizational chart, adjusting to reflect two divergent product lines. In practice, it was the moment the company's naval engineering legacy, the very reason General Motors had entered the diesel business in the first place, was formally set apart from the business that had grown to eclipse it entirely. The engineers who had once worked under a single roof, solving submarine and locomotive problems with shared knowledge and shared urgency, now belonged to two separate divisions, chasing two separate corporate mandates, inside the same company that had once seen no meaningful difference between them. The Navy's engines would still get built. Cleveland Diesel would go on, in the years ahead, to play a real and important role in America's submarine fleet through the coming war. But something else, something harder to name on an org chart, had already begun slipping away. The engine still ran. The name did not survive. Through the early 1940s, as the United States entered the Second World War, the diesel engineering lineage that had once carried Alexander Winton's name proved its worth in the most demanding conditions imaginable. Cleveland Diesel Engine Division's descendants of the original Winton architecture powered a significant portion of the U.S. Navy's fleet-type submarines through the Pacific Campaign, engines that, unlike some of their wartime competitors, earned a reputation for reliability under combat conditions. Where the rival Hooven, Owens, Rentschler diesel had developed serious reliability problems once installed in operational submarines, the GM-descended Cleveland diesel engines held up. crews trusted them. That trust, built over more than a decade of incremental engineering refinement, mattered more in wartime than any sales figure. But reliability in combat did not translate into corporate prominence back home. And by the time the war ended in 1945, the company that had once been called Winton Engine Corporation had, for all practical purposes, ceased to exist as a name anyone outside a small circle of naval engineers would recognize. The paperwork told the story plainly. General Motors' corporate structure by the mid-1940s listed two clear successors to Alexander Winton's original engineering legacy: the Cleveland Diesel Engine Division, handling naval and heavy industrial diesel work, and the Electromotive Division, no longer just a corporation within a corporation, but GM's dominant, headline-driving locomotive business. Nowhere on an organizational chart, a press release, or a locomotive nameplate did the word Winton still appear. The name that had once identified bicycles, then automobiles, then submarine engines, then the diesel-electric revolution itself, had been fully absorbed into the identity of the company that acquired it. This was not a bankruptcy. There was no auction of assets, no liquidation sale, no dramatic plant closure making front-page news. Nothing about it looked, from the outside, like the collapse stories that define so much of American industrial history. And that is precisely what makes it such an unusual case. Winton did not fail. Winton disappeared by succeeding too completely inside someone else's name. Consider the numbers, because they tell the real story of where General Motors' priorities had settled by the post-war years. Electromotive Division, by the late 1940s, was manufacturing diesel-electric locomotives at a pace that was actively driving American steam locomotives into extinction. Railroad after a railroad converting entire fleets to diesel power, chasing the same lower operating cost the Pioneer Zephyr had first demonstrated back in 1930. Cleveland Diesel, meanwhile, continued producing engines for the Navy's submarine fleet, but as a comparatively small, specialized operation, respected within naval engineering circles, essentially invisible to the American public, and dwarfed by comparison to its locomotive siblings' soaring production numbers. The human cost here was not layoffs or a shuttered factory. It was something quieter, an erasure of institutional memory. Engineers who had once identified themselves as Winton men, carrying forward Alexander Winton's original obsession with mechanical precision from bicycles to automobiles to submarine engines, now worked for divisions named after the applications that had absorbed his legacy: Cleveland Diesel, Electromotive, corporate names describing what the engines did, not who had built the foundation that made them possible. Within a generation, most people working at either division likely had no direct memory of Alexander Winton at all. His name survived mainly in company histories and Navy procurement records, not in the daily language of the men building the engines. The submarine engines his engineering lineage had made possible were still running. The locomotives his two-stroke diesel breakthrough had made possible were reshaping the American landscape, mile by mile, replacing steam across the entire continental rail network. By almost any measure, the technology Alexander Winton had pioneered was more successful, more widely deployed, and more consequential to American life in the late 1940s than it had ever been in his own lifetime, and almost none of it still carried his name. That is the particular shape this story's collapse takes. Not a company that failed, but a name that won so completely by disappearing into something larger that its own origin became a footnote. The submarine that started this whole story, and the locomotive that ended up carrying its legacy forward, were now running on engines built by divisions that had never once been asked to explain where their engineering came from. Today, the name Electromotive Division, or EMD as the railroad industry has called it for decades, still means something. Locomotives descended from that original Winton lineage two-stroke diesel architecture remain a fixture of American freight railroading. Their low, unmistakable growl, still audible at grade crossings and rail yards across the country. General Motors sold the division in 2005, and after passing through private ownership, EMD became part of Progress Rail, a subsidiary of Caterpillar, in 2010. a modern industrial giant now stewarding an engineering lineage that traces back, in an unbroken line, to a Scottish machinist's bicycle shop in 1890s Cleveland. Walk into a rail yard today and watch a diesel-electric locomotive idle before a freight run, and you are, in a very real sense, standing next to Alexander Winton's original engineering bet, refined, scaled, and separated from his name by nearly a century of corporate reorganization, but mechanically descended from the same core insight that once justified a Navy submarine contract. The paradox is almost too clean to be believed. The engine built to save American submariners' lives beneath the Pacific became instead the engine that quietly ended the age of American steam railroading. The Cleveland Diesel Engine Division did not disappear either. Though its path looked very different from its locomotive siblings, it continued producing diesel engines for the Navy through the post-war decades, eventually merging into other General Motors industrial operations before the naval diesel business was largely phased out as nuclear propulsion transformed submarine design in the 1950s and beyond. A technological shift, explored elsewhere in this series, that made the entire category of diesel-electric submarine propulsion a wartime relic rather than a modern requirement, where Electromotive's descendants still roll across the country every single day. Cleveland Diesel's naval legacy survives mainly in archives, museum collections, and the preserved engine rooms of retired submarines now open to the public as floating memorials. And here is the footnote almost no one expects. Among diesel locomotive enthusiasts today, a genuine active community of rail fans, historians, and mechanics who restore vintage EMD locomotives as a hobby. The deep engineering history connecting their favorite machines back to a U.S. Navy submarine program is often treated as trivia, a surprising factoid traded at model railroad convention, rather than common knowledge. Ask a devoted EMD enthusiast about the 201A engine's horsepower curve, and they can likely recite it from memory. Ask the same enthusiast why that engine was originally designed the way it was, and the submarine connection often comes as a genuine surprise. Proof of just how completely the railroad application eclipsed the naval origin story in the public imagination. Stand today at a rail crossing in the American Midwest, not far from where Winton's original Cleveland Engine Works once stood, and wait for a freight train to pass. The ground will vibrate faintly before the train itself comes into view. The same low mechanical signature that once announced the Pioneer Zephyr's arrival at small-town stations across the country in 1904, the same underlying engineering principle that once kept American submariners alive beneath enemy waters in the Pacific. Two applications, one engineering bloodline, and only one of them still carries the growl into the present day. Winton Engine Corporation did not fail. It did not go bankrupt, and no headline ever announced its collapse. It simply succeeded so completely in a market nobody expected it to dominate that the market it was actually built for, the one bolted into a submarine hull in a Cleveland testing shed in 1929, quietly became somebody else's division and somebody else's story to tell. That freight train still rolling past the old rail crossing, still carrying buried deep in its engine block a piece of a submarine program nobody writing today has ever heard of. That's Winton's real legacy. See you in the next one.